All right, IT286. Okay, section 1 we completed, quiz. Okay, section 2 we wrapped up the platformer. Those enemy controllers, token controllers, looked at the tile map, did an intro first person shooter, like flew through the scenes. It looks like I forgot to get the video up. I have to get the video up for the UIs, but last class was looking at intro scene, lose scene, win scene, which had this screen space UI. And we went over all the details, including the scripts. And then I went into the main scene and I was picking apart all the scripts that had to deal with the HUD, which screen space UI, heads up display. So if I click play, we've got stuff in the top corner, the tab key that creates the pause menu. We've got this radar system where they call it the compass. It shows you where the enemies are. We've got a crosshair, we've got some notifications in the middle, we've got some objectives up at the top left. We got health, and let me see if I crouch the status. No, I thought maybe this icon switched between like crouch and jump, but it doesn't. And we have our gun status, our bullet status. And so all this is screen space UI. All this is going on in the game HUD. Then when you press the tab key, it was the in-game menu. We covered that. And then I said, all right, since we're just talking about UIs, let's talk about the world space UI. Let's go to a hoverbot and let's click its health bar pivot. And so we had to go over like a little bit of the enemy controller, and here that the world space health bar was like, this is like the super important part of it, how it's managing this UI. But ultimately this is just a canvas UI, but it's in world space, sitting atop the robot, inheriting the transform of the object above it. So now we knocked out the easy scenes, and we did like a gameplay walkthrough of the main scene. And then I kind of went in and started covering some of the UI just because we're talking about the UI. But I didn't kind of, let's just take a look at the world visually, and so we understand where everything is. So if I keep zooming out, this is that big screen space UI. This sun here, it seems to be okay. So under level, we have our directional light source. And let me see if I rotate it. Yeah, so you see how it's like changing where the sun is in the sky. That's a pretty common feature these days. And here is the 3D level sitting at world space 0. And if you look around, we have this whole world around us. So somewhere there's got to be a skybox. So under level, we have room 123. What's high step? It's just this box. Interesting. So this must be like a template. This must be like the walls and the floors and all the little, it's like all the parts of the kit just kind of sitting together if you need to edit the level some more. So we'll look at like the level pieces. But right now that's not what I was looking for. We have some VFX. I wonder if it's under the lighting. So this is the color. It's tinted. Everything's tinted. All the main light sources are tinted red because we're in this like lava world. We have some soft shadows. I wonder if it's under game manager. No. So we have our nav mesh. We have our nav mesh, which is for the AI agents. That's this light blue mesh. the event system for our UI. We have our objective to kill enemies. We have the player. We have some enemy turns. We have the patrol pass, the pickups. All right. So the only other place it can be is in like projects. Oh no, you know what? I bet you it's in reflection. Okay. So what happens with these are our main scenes, and notice we have like if you have like advanced lighting, you'll have this like lighting file. We're not going to get too much into advanced lighting in this class, but it is a separate asset. And okay, nothing crazy is turned on. Then when you go into this folder, so each scene that either has nav meshes baked out based on the level mesh, you have these nav mesh surfaces kind of stored. So each one of these are different. And then you have a reflection probe, which is dealing with lighting. And the texture shape is cube map. So these big cube maps. Sometimes when you see this like big world around you, either it's a big cube or it's a big sphere, and it's just a texture wrapped onto it. And as I'm looking here, like this is the reflect. So it's like the reflection probe is kind of like when your materials. I'm gonna have to move it to talk about materials. They have a specularity and a highlight and like a reflectivity because you don't want just flat objects. So we have different types of shaders, and so if I just make a sphere, it looks like it's using this universal rendering lit material. Lit. Okay, this one. So, okay, got it. So it's under packages and universal render. So it's like these are like external assets, and so you can't. It's all grayed out. You can't edit them. So let me create one. It's using the universal render pipeline. We might have. Now I'm gonna have to jump into materials. Looks like they don't have any art materials. Okay. Oh, so here's the skybox that I was looking for. So this is the big panoramic image that's being wrapped around the whole world, and it's just looks like it's like a 360 degrees. It's being like wrapped onto a big sphere. I'm just looking up because usually there's like a pinching with the texture at the top. So this big panoramic image, it's an illustration, so it's being wrapped into the lighting situation. So that's good, but I wanted to hunt around for a lit. Okay, here we go. Jetpack. So I'm just going to duplicate this one and just going to clear out its textures because we haven't talked about any of this yet. So I just want to make a basic one with no materials just to talk about it. All right, perfect. So let me go back to my sphere. And I'll put this jetpack back on this material onto it. And since I made the material, should be able to edit it. Nice. All right, so this is an advanced material. Materials are assets, and They are, you can think of them as like abstractions or wrappers to shaders. So notice it's like referencing a certain shader here, and there's a whole bunch of shaders. Usually we start off just with the standard one, but it looks like they're using like this universal render pipeline, which is like the next stage. So the standard shader has been used forever recently. It's called PBR, physically based rendering. It's been like the standard de facto of doing shaders, making realistic, photorealistic materials. And we're kind of, I don't think we're, the universal render pipeline is just like, it's Unity's attempt to like expose more of the rendering pipeline. Usually you only had like materials and shaders, and you couldn't touch the rendering pipeline. You couldn't touch all these different parts that have to go through the graphics card to render everything to screen. And now this is their attempt to like be more kind of open source and make more parts of the render pipeline exposed to you. But the gist of yeah, if I look at, it's just more is exposed. Okay, this is the standard shader. So standard shader, the basics of it is you have something called albedo or base map, base color. So albedo just means diffuse color, base color. So here it can be white, it can be red, green, anything along. So I'm using this color wheel, and you notice as I'm moving it, the red, green, blue values are changing. Just some background now on color. So it's going to be a vector 4 floats, but we're dealing with RGB A for alpha, transparency. And you have 0 to 255. Remember, we count from 0 in computer sciences. 256 values of red, 256 values of green, and 256 values of blue. If you multiply them together, this can express millions of colors. More than enough for the human eye to process, and it feels like the entire like spectrum of color. And it's a nice trade-off between the amount of memory size that each color takes up, and the amount of color range that you can express. So 256 values is 2 to the 8, 2 to the power of 8. So we do powers of 2 in computer science, do the binary system, and so this is why we call it 8-bit color. So we get 8 bits of color information for red, for each channel, red, green, blue, alpha. So 2 to the 8 bits. And so really it's 8 times 4, or 32-bit. I would say it's 32-bit color, but it's 8 bits per channel. You may have heard of 8-bit color for Nintendo, 16-bit color for like Genesis. And we've been in 32-bit color for a while, and it's more than enough color. We don't need to go up to like 64-bit color. Some other things to note is you can also represent color with a hexadecimal number. We're not going to do that. Usually when we change color by code, we're going to use 0 to 1, a different scale. So 0 to completely off and 1 to completely on. And also, just for completeness, we have another way to represent color. That's hue, saturation, value. Notice as I move here, the H value is changing. Notice as I move this way, the S value, our saturation, how saturated is the color. And this way is value, or how much light is falling on the surface. So complete shadow to complete illumination. But we will be using RGB 0 to 1 when we code up our colors. Base color is really important. Metallic has to deal with how much of a metallic surface this feels like. Since this object is being, let me just make another shader real quick and see if it's not as another material. Sorry. See if it's not as influenced by the environmental lighting. So this universal render pipeline is, it's hard to see the differences with each little, you can't use standard shaders in here. Okay. Gotcha. Whenever you see this hot pink magenta, this is like the shader world's error code, because when you write shader code, it's really hard to debug because you don't. Maybe we'll look at the shader graph in this class, but we're not actually going to write shader code. But maybe it's worth just looking at it quickly. But I can go to edit, and this is like the properties of the shader that are being exposed. And is it compile and show code? Okay, cool. This is what the shader code looks like. So at the top here is just the properties that are being exposed that you can tweak with materials. This starts the actual shader code. So there's like level of detail, tags, what type of render type it is. There's like passes, how many passes per render cycle. You could think of render cycles like update loops. Actually, in fact, every time we run the update method, we're like updating our graphics. So at that point, the shader code is run as well. And there could have to be like multiple passes per cycle, per update loop. But normally there's like one main pass. Normally we're using what's called like forward-based lighting. And a lot of this we're not going to get into, but it's good to see if you ever want to dig deeper and you're interested in becoming a shader programmer. This is about the depth buffer. Like you have to know like how far the z distance from all these pieces of geometry that you're rendering, so you know how to like overlap them on top of each other when you render them to camera. The type of blend modes, we just do like kind of normal, like one gets rendered on top of another, but you can do different blending, kind of like Photoshop blending. And so it's like, what type of hardware are we rendering to? Are we using DirectX or OpenGL? And we have vertex shaders and fragment or pixel shaders. And these are basically like little sections. You can write code for vertex shaders or pixel shaders, fragment shaders, and they run at different steps through that pass, through that cycle. And usually, let me just check quickly if there's like some type of interesting graphics for this vertex shader. So, yeah, I think this one might suffice. So what's happening here is like every 3D model. So everything you click on here that has a 3D model. So for example, the turn. Let's move down here. Yeah, the turn doesn't have its rendering. Okay. Here we go. So if I go all the way down here, this turret bottom has a mesh renderer. So this component here deals with rendering. So there's just a piece of geometry, a bunch of 3D model just for the bottom, one for the centerpiece, one for the top piece. That's not. Looks like there's three main render parts. Maybe there's stuff in here. These are joints. We haven't talked about joints yet. So there's three main pieces of geometry that are broken up into three game objects, and each of those get a separate material render pass as they go through. But what does it mean for each one? So when they go through a vertex pass, first the vertex shader, it's like, okay, what's the main camera? So the player has the main camera, and it's like, what of this whole entire scene are we seeing from the camera? So the camera's way over here, right? And it sees this wall, this wall, this wall, and this floor, and it might even see stuff beyond it. It might render this stuff, because if you look in the frustum, this large pyramid shape, this is everything that the camera sees. If geometry is outside this, it doesn't get passed through the render pipeline, because why render it? It's off camera. But you do have a lot of geometry, like all this stuff here, which is actually blocked by this big wall. But in a basic render pass, it's like, hey, all this is in the camera view, render it out. It's just this back stuff gets rendered first, and then this stuff, and it's in that like Z buffer I was talking about, that distance, and then this stuff, and then this big wall gets rendered on top of everything. And so it's almost like there was no point in rendering all this, but since you have to render every frame super fast, you can't always put a lot of logic to like filter stuff out if it's stopped being rendered. So all this stuff has to go through the vertex and the pixel shader. So what is the vertex shader doing? It takes a piece of geometry and it figures out how to render each of its vertices. So if we take this sphere, and there's a way to turn on the components of it so you can understand, okay, shaded and wireframes. So this sphere has a mesh filter component, a mesh render component. Mesh filter contains all the geometry parts. So the geometry actually means the vertices, the dots that exist in this piece of geometry. And between two dots, you can draw an edge or line. So the edges are part of these components as well. And then if you have one edge, two edge, three edge, you can draw a triangle, and the triangle is known as a polygon, and it's the polygon that's getting rendered. So actually behind the scenes, it's just like an array of vertex locations and then an array of triangles that map to those vertex locations. So anyway, you could think of vertices and polygons, and we deal with triangles. Everything gets what's called tessellated. Or triangulated, and even if this thing was made out of like squares or quads or other shapes of geometry, everything gets chopped up because the graphics card can only process triangles. So once you know that, and we go through to vertex shader, it's basically like saying, okay, where are all these vertices of this piece of geometry, in this case this sphere, where are they located in the world in respect to each other, in respect to the camera? So just pretend that these three dots represent like these three dots here. And this is my current camera view. Like, yes, I'm in the dev camera, I'm not in the main camera, but even my camera is getting, even this little viewport in Unity has to be rendered out, every single frame, or otherwise how is the Unity editor going to paint to the computer screen and show you where you, the developer, are at? So this is happening here as well. So the first thing, it's like, okay, for each vertex in this whole sphere, where are these dots located on the screen, on the computer screen that the camera is rendering, right? And so let's pretend this little square is like our computer screen. And these dots are just like three dots, three vertices on that sphere. And so then we get piped through the geometry shader, and it's like positioning. You can do like a lot of interesting effects and animations and movements, but it's ultimately you're like, the shader is running this code. Like, oh, here, after all the code that I'm running, here is where vertex number vertex number 123, 124, 125 out of a 500 vertex sphere or whatever. Here's where they're located in the world. And if you project them onto the camera, into screen space is my monitor space, is this little rectangle viewing into this 3D world. Eventually, when we go through all this rendering pipeline, we go through all these shaders and pipe all this 3D geometry through every single frame. And even right now, we're running frames. Even though we're not playing our game, we're using the Unity editor, it's still running through frames. It has to figure out where these dots, these vertexes, go on the screen. So it goes here, here, and here in 2D space on the screen, X left and right, Y up and down. We have transitioned from world space to screen space while we're processing the shader in vertex shader. So it's almost like for each 3D model, each 3D mesh, let's go through all the vertices, and where should they be in screen space for this camera that's responsible for rendering to the screen. and then it gets piped through. These are other stages that we cannot code. So we cannot code in the geometry shader phase, only in the vertex shader. And we cannot code here in shape assembly. We cannot code here in rasterizer, but we can code here in fragment shader, and then we can't code here. But when you use the render pipeline, these parts of these stages have been opened up to you, so you can like do more interesting things in the pipeline. So that's why they call this like render pipeline stuff. Their pipelines being opened up. But traditionally, you can only write shader code here in the vertex shader. You can only write code here in the fragment shader. So what's happening is vertex shader, where all these vertexes are. Let's do some stuff to it, whatever the shader code says. Did the user press the left arrow and move the character a little bit so the world space for that piece of geometry got updated? After all that's been figured out, okay, where are the dots on the screen? And how do we, based on this piece of geometry model, what are the triangles that we have to make up between these dots? And based on these triangles, these polygons, the actual shaded part of the geometry, what goes on the screen to the camera, and now we start moving into the pixels of the monitor. So everything that you're looking at right now as you're watching this class, you're looking onto your computer monitor, which is just a big 2D array or a big matrix of little squares, little lights. And each of these small little lights can broadcast some type of color information, just like I showed you in this 2-bit, 8-bit per channel or 32-bit graphics. All of those little pixels in your monitor can represent one of those different colors, and the pixels are so small that it blends together into what looks like continuous graphics to you at the macro level. Now, that's where this rasterization part is. We're still like thinking about the geometry, the little triangles that are facing the camera that are in screen space being drawn. That used to be sitting in 3D world space. We're drawing them into the flat screen where the camera is projecting onto the monitor. And then the next step is like, okay, which pixels of the monitor is this triangle inhabiting, or these two triangles inhabiting? And this represents the pixels. Okay, so think of a 2D array. I know we just covered how to like do elements, how to like grab indices of a one-dimensional array, but two-dimensional arrays just work like rows and columns in a spreadsheet. You just say, hey, go to this row, go to this column number, and that number in a 2D array represents that element, that pixel. So we list out all these elements within a 2D array, all these pixels that these triangles are currently, we're only supposed to really do one triangle at a time. They should just draw one everywhere else you see it's like one triangle. I don't know why they drew a line right there. But this is, imagine this is one triangle, and then here's the shape of that one triangle on the monitor's pixels. We don't have straight lines anymore. We just have a bunch of discrete little squares. That's great. Now we say, okay, we know the pixels that this triangle is inhabiting. So like this one, just imagine a bunch of little squares over this triangle that we're about to figure out how to render to the screen. And then the next stage is the fragment shader. So then it's like, okay, from the material and the light sources in the scene and the light sources and the materials and whatever not post because we're not in post yet, whatever effects, visual effects are being added to the screen. Usually it's just the light source and the material on the 3D model. We can figure out what color each of the little pixels should inhabit. So here, this is darker shades of blue, but as you notice, it's actually turning light. There's some type of light source over here, and it's lighter on this edge. It's still lighter, darker, darker, darker. I'm moving away from the light source. So there is a slight range of blues on these little pixels that will inhabit this. And if you can't see it there, just move, like look at this one. There is a range of blues here because the light source is coming from over here. Right? And so the fragment shader, which we just opened that for us to write shaders for as well, we'll say, okay, what's the lighting like on this triangle for each pixel? What's the material like, the base color, the metallicness, the specularity? And ultimately it's like, okay, assign it, here's the RGB value for this tiny little pixel. And it does that for all of it. And then it just goes and it fills up like a buffer, like a whole 2D array of like color information. And when it's time to paint the computer monitor, it swaps the buffers, the current buffer that's like turning on all of the lights on your computer monitor. It'll swap it with the buffer, the 2D array that we just built, so all the new color information and all the little lights on your computer monitor will change to represent that new frame of the game. And this is across the board. Like, this is how, like basic apps on your operating system and websites, they're not usually on 3D, so they're not as elaborate, but this type of graphics processing is happening even at the 2D level for like basic applications. And then there's like post-processing and blending, that if there's like the next stage, depths of field and vignettes or whatever. And in this situation, we keep painting over areas. So remember I said this big wall, like if you look at the player camera, there's a big wall right here, but it was painting all the stuff behind it. And adding, and then eventually it said, no, this like gets the final paint, the final color choices for these pixels on the monitor in this little game window. So that is a huge quick run through of shaders, and this is kind of what the shader graph looks like. You can like plug, you don't actually have to write the code. You can plug nodes in. So this one is like, okay, take the position and put some Vernoid noise onto it and multiply it by some normal vector, and then multiply that by this number that can be represented as a slider in a UI. And then take this and add it to the position again. This is the world position, is the object or local position. And put them all together into the world position. So all this calculation is done at the vector shader level to give the final world position of each vertex. All of this, I should have probably said that. For each shader runs through, the weirdness of shader code is that when you write vertex shader code, it just, whatever code you write runs through and does that code to each and every vertex. It loops through it. So this, everything I just explained here, it does this, it loops through, does this all to each and every single vertex and updates its world position. And you might get some funkiness like this, turn a sphere into this weird mishmashy star shape. And then the fragment shader is only run per pixel. So it's like, okay, here's the number of pixels, and it looks up like the position on the 3D object to like reference the texture material stuff, the UV space, which you yet to get into. So this is a very complex and convoluted topic, and it really like deserves like its own class. I just need to introduce you to it, but let me know if there's any questions. So ultimately, materials exist to wrap up all that insanity of the shader, which actually I didn't even finish. So we have our vertex shader, and we're saying we have different data channels for vertex normals, texture coordinates, UVs, which I'll talk about in a little bit. And looks like we have some buffers there being set up, and just crazy like lower level. It looks a lot like, it functions a lot like C, but there's also some like kind of assembly level, like lower level stuff going on in language. But most of the time, it's written in a very similar language to C. And it's a very complex one, so it's crazy. But we start, if you ever take a shader class, it starts with very basic shaders. So anyway, a material wraps all that up. Material is just like, hey, I'm going to use this shader, and this shader already has properties that are exposed, and I could tweak them. So all this stuff is all properties the shader is exposed. You just can tweak it in a nice GUI through the material. All right. Now, some of the main stuff, like base color, I just turned it blue. Looks like I was messing around with the environment's not like the best to look at because it's just kind of this checkerboard. This checkerboard material. So, for example, like this mesh, this doorway here, it's wall dark gray. And so it just has this. This one happens to be. Let me turn off the shaded view, the wireframe view. This just has a base gray color applied to it right there, and it's no metallic, no smoothness. It's just flat. But if I zoom in and grab this thing, the triangle sign, completely different piece of geometry, completely different game object. And the material is called sign green transparent. So now we have some transparency. It's not opaque. So alpha will be impacted here. And I can move alpha, and you can see it goes from opaque to transparent, which is a much more expensive rendering. That's why it defaults to opaque. And let me bring that back up a little bit. And it's just got a green color on it. It's a very basic. It's got some emission. It looks glowy. It's got some emission color on it. But if I click on, oh, it's so hard to click this wall. There we go. Medium. Okay, this wall. It's got little chunks of 4 meter. Okay, so there's a modular kit. You can just pull out a piece of the wall and it fits perfectly. So this one has 2 materials assigned to it. Wall gray and wall dark gray. I was trying to figure out how they get in this little checker pattern. So if I pick wall gray, yeah, it's just dealing with, okay. So this mesh object has got 2 materials. You can have more than 1 material. Usually there's 1 material per mesh, but you can have more than, looks like instead of just breaking this up with a texture, like 1 material, but like a textured material to get this checker pattern. Looks like they're just applying materials based on different faces. So if I look here, you could do that like in your content packages like MyMX, Houdini, wherever you like model this stuff. You can select faces and assign different materials. Then each face says, oh, I get material wall gray, and I get material dark, this should be dark gray, and this one's gray. So we're just applying different flat colored materials per face. So that's one technique to getting like a variety of colors onto an object. But let me just look at like this enemy robot. Let me get rid of these gizmos on it. I can't even see anything. Okay, so this one is probably using this. Let's look at the top of this thing. The bottom joint, the top. Okay, skin mesh render. Skinned is different than mesh render. It just means that it's been skinned to a bone system. This is a bone system that in their content packages like Maya, it's for doing soft body animations. And it's an animation technique where you animate on these bones, and the bones are like controlling the positions of the meshes, coincidentally through the vertex shader. But just to know what they are. It's a different animation technique. It's used a lot, but we don't do it in Unity. It's done in the content package. We bring it in. But that's just with the skinned mesh render. It means here's like the bones. But what I wanted to look at was its material. So here is something a little different. We actually have textures plugged in. All right, so it's got a metallic texture map. It's got high smoothness. It's got a texture map plugged into base map. So if we click on that, this is what the texture map looks like. So now, this is very different than how sprites are rendered to screen. Now, sprite is usually like just rendered like directly to camera on like a little like square or rectangle. Now notice this texture type is default, not sprite. So here we have a 2D space. It's just a flat texture. And somehow this flat texture information is being mapped onto a 3D mesh, a 3D surface. Right? And this is the process of called UVing. So this is how you can get more complicated materials. Instead of just like a flat color or assigning multiple materials, you could say, no, here's my texture map, like a complicated set of texture that we're going to map to our diffuse, our base color. And you could do this to any of the other types of properties, but here's base color. So it's giving these darker areas, and then notice there's like a fading, like wear and tear on the edges, like a lightening. It looks like there's like a little rust here on the edges, like a reddening on the inside. Here's like a bolt, like black, dark grays with softening. So let me see if I can figure out. So the bolt happens to be down there. It's kind of small to see. So this like big circle thing here is the top part here of light grayness. Like this big area here is this area here. I could just see it in the shape. And these like these dark black eyes are these here. Like you can see the relationship to them. This bolt here is this bolt down here. Let's see if there's anything else I can recognize. This top like bolt thing is either this thing or this thing. I don't think it's this one, but you could start to like kind of identify the 3D surface, like where it connects in this 2D texture. So the question is, how do we go from a vertex or a triangle, a little polygonal triangle that's sitting in 3D space? How do we get it to map to a 2D space? And I don't know if there's a way to. I don't think there's a way to. No, I was looking if there's a different way to turn on. So you can see like the wireframe there as well. This is UV space, and it's called UV because they didn't want to use X and Y to confuse you with the X, Y, and Z that's out in 3D space. So U goes along the horizontal axis. So U of 0 is over here on the left, all the way to a U of 1 on the right. And a V at the bottom is a V of 0, moving up to a V of 1 at the top. So every little triangle in addition to having, I should say every little vertex. Every little vertex, in addition to having a position in the object space of this model, like we look at the center of it. So if I press the W key, the center of it happens to be down here, like when you move it. And each little vertex has an XYZ position in respect to its object's center point, which is down here. This is called object space. We're not out in the world space. We're out in relation to its little pivot point of this object. So every little vertex, every little dot has a position, an object position. And it also has a normal, like how hard. Notice that we have like a hard edge along here, but a soft edge over here. And that's determined by like the normals of each point. Like the normals are like, what's the orientation of this point on the surface? It's somewhere pointing out like this. Let me see if I have a good image for that. Let's see, which one do I want to use? This one looks pretty good. So each little dot, you can kind of see the orientation where this face, if you look at this big face on the object, it's kind of pointing out along the, see this red line here? This dot is sitting on this part of the surface, these 5 triangles, and it's pointing out this way, kind of toward the camera, but off to the right. And this one's doing the same. It's pointing kind of toward the camera, but to the left of the camera. Now, notice that there's some hard edges here. So like this vertex is pointing this way. It's a sharp transition from this one and this one. So since there's a sharp change in the angle from this normal to this normal, we're going to get like a hard crease here because it's a big change in the normal. And this cube's actually kind of a good one. So like here we have a big flat face, but we have like rounding, and these would be like a soft transition in normals to get this rounding area. So anyway, normals are like the direction of the face in the vertex. We have vertex normals and face normals. It's just kind of showing you like how they're oriented, which direction they're facing, and that's how they understand how, like, what type of lighting is hitting them, and also how to do like how closely related are they to like the faces, the triangles around, and to how to do like a hard or a soft shading transition. But anyway, that's normal information, and you like normals will come up a lot when you're in computer graphics. There's also this idea of tangents and cotangents, not as used as much. And then there's this idea of texture coordinates or UV coordinates. And so each little dot, besides having a position, object position, and object normal, will also have a UV, a texture coordinate. So it's like saying this little dot here within this UV space. Let's just say this little dot is like somewhere here. So this is like a U of like 0.25 and like a V of like 0.75. It goes up high, 0.75. And it doesn't go to the right too much, 0.25, 0.75. So these little ones here that draw up this little triangle that is somewhere right around here will have a UV of like 0.25, 0.75. And so they'll have UV information. And so that's how they look up. They look up their position in this texture map. And they look up the color information. Oh, for this little pixel and this little texture, the color information is RGB, whatever. And that's how this gets color, that gets color information. And then every little pixel, remember when this gets turned rasterized and it gets turned into little pixels? For each little pixel, you could say, hey, I'm this far from this vertex, this far from this one, this far from this one. I could tell where I am in my UV space. So it blends. It takes like an average of the UV positions of these vertices. It goes, oh, the little pixel is sitting here on this triangle. And it says, okay, this is my UV position. It looks up the color information and it just paints that little pixel. So that's that fragment shader. And texture coordinates or UV coordinates come in a lot because they use textures. like this to get really elaborate um, rendering effects. And so here's the textures for it. So we ended up going into shaders and materials in the render pipeline to explain some stuff. So we pretty much spent quite a bit of this class on that. I just stopped briefly. If there's any questions. And so it's kind of like a survey class. Like we'll see how much we dive in for the rest of the class, but just for you to understand what's happening. And then there's this metallic map, which you could have just gotten away with a solid color. But anyway, it's just saying, hey, the metallicness, the shiny metallic nature of this material is a dark gray, which means it's getting kind of close to metallic, but not like 100%. And normal, remember I was talking about normal maps? And so this one doesn't look like it has much information, but normal maps are a way to fake even more like texture details on the surface than is actually up here. So like it's expensive to use geometry, and you see like how much vertices are needed just to get this shape, and it's kind of like a low poly game asset. And so you don't want to like make it, this is already kind of expensive on the render situation. So if you want to make like stuff that looks even nicer, like it's made out of more vertices, more polygons, you'll like apply like a normal map on top of it. This one doesn't have a normal map, but like it's a way to fake more geometry detail. It's not there; you're just faking it with textures. I'll see. I don't think if anything in here might be using a normal map, but it's very used a lot. And occlusion is just like darkening of places. It's like what is self-occluded. So anything that's dark gets less light information. So here he says I wrap down. It's like if it didn't have self-occlusion, it wouldn't look as realistic because it doesn't look like it's dark in here. So the way light works is like light's coming in the real world, and if stuff is like crowded and there's like a lot of surface around it, the light's not going to bounce up in here as much. So you'll get a lot of light hitting the top because it's in direct view of the light source, but you won't get as much light coming down here, hitting up here, and then getting in here. So in reality, you'll get self-shadowing, you'll get self-occlusion, and so that's what these occlusion maps are for. I think that's like pretty overkill. Usually maybe, I don't know, something like that. See, it's more darker up here and it gets so lighter. So occlusion maps are important to get that physical reality. And emission has to deal with a glowiness, like self-glowiness, probably this like light source in here. Let me turn it on. How it is. So there is a glowiness to it. Yeah, an emission map here. Interesting. That's the body. Oh, there's two materials. Got it. So this whole thing has a body material, and then here's the eye material. You gotta be careful. So in this case, there's more than one material being applied, and this eye material is being applied to this glowing part. Notice there's this crazy emission color on it, so it looks like it's glowing. But you could like make it blank and stuff like it's alive. You could just animate these colors with your code, or with an animation file as well. And this is more like tech art, more like it's kind of moving into a different class. You just need to know how to handle stuff. You need to know how to deal with materials and shaders in your project. So I'm getting these like bad hiccups. So that's a surface shader, standard shape. And there's different workflows, but the standard one's metallic. Oop, I'm gonna have to just mute myself for like a minute. These hiccups are getting bad. Um, just give me a minute, but let me know if you have any questions. Um, I think it's a good thing I might be wrapping the end of like looking at this level because these hiccups are starting to get to me. Um, so this big panoramic image that's being wrapped here is this skybox material right here. And it's being applied spherically, and it's somehow being applied in the lighting. And I think it's being applied in the reflection probe. No, this is just the picking up reflections on objects, and you give it some type of material to apply reflections that look like this. Sorry for the hiccups. You can search in the, let me see, some skybox. Oh, I forgot. You can, you notice it, you could search up here too, but I forgot an interesting thing. You can actually go into skybox material and say find references and scene. You see that search? Nothing. Passing. So project settings and graphics. I bet you it's going in there. Okay. Just render pipeline global settings. So these are these asset files, and they're like tweaking the big render pipeline settings. And we're not going to get into this too much in the class. It's purely advanced stuff. But I just wanted to hunt down. This post processing profile is interesting. You can like tweak like bloom, vignette, so in the game view. So you can see there's like this film graininess going on. Film grain. You can turn it off. You can tweak it. Now we don't have that film grain. Motion blur. Blooming just means like light blooms coming from light sources. Maybe there's like a lighting window. Rendering lighting. Okay. Means in lighting. There is a lighting window, yeah. Yeah, here we go. Environment, skybox, got you. So this is a skybox in the lighting tab under environment, applying the skybox. That's how you get this this big skybox everywhere. So it was under lighting window, if you're interested. The only thing I want to cover for, I think so you're taking me over, is like we have this VFX here. So in the game, I click play. You have this like lava and dust coming up, and that's this VFX systems. So you don't see it too much here, but you see these little um, lava specks coming up. Here you can really see them. They're all over the place. All right, this is a VFX just applied globally to the entire level. So you can click on one, and we have this particle system component, and there's a lot of tweaks you could do to the VFX systems. Have like a whole thing like that. But the cool thing is you can like simulate, and they have like their own timeline, and so they're like simulating, and that's should be what these are if I pause them. Yeah, you can pause it, and then you can simulate them, and you can mess around with them. So it's just a big generator down here, generating particles that are floating up, and you can like change their size, and you can really see them. Maybe increase their speed so they get a little bit further up. But you see that they're just little flat graphics. You can't render all this as 3D geometry. So particles have an interesting thing. They're little 2D graphics or sprites, but they're always facing the camera. No matter how you look at them, you never see them on the side. So just like that World Space UI, like the little health meters on these objects, they're always facing you, the player. You don't see them at a weird angle like that. And so normally VFX stuff aren't little cubes. They're like but you can make them look like smoke and water and fire and anything you need as far as visual special effects. And then dust, I'm not sure where the dust is. It must be like this super small. I can see at the base of it is right here. I guess it's these little glowy things. So I'll like ramp them up. Now these are okay. They're just these little square things too. Normally it's like circles or squares or stuff, but there's so many of them, they overlap on each other. They get like this emergent behavior, like they really do look like smoke or water or fire. Anyway, that's the VFX. You can mess around with them. I guess my settings didn't go through. Oh, there. So that was these two VFX for dust and lava. And it's just a particle system that's a component, and there's just a whole bunch of little parameters you can tweak. But they're all simulated. They're basically just a whole lot of sprite graphics that are part of like the physics system, and wind is moving them, and they get a velocity and momentum, and they can change colors and sizes over. There's a bunch of stuff you could turn on and tweak. Each of these open up, and you could tweak it. So just the size over lifetime has its own graph, color over lifetime. Noise looked pretty complicated. But that's it for today. And so we went into looking at the whole main we actually spent a lot of time diving in and talking about the mesh render, the mesh filter, the mesh render, the shader pipeline, vertex shaders. We're talking about vertex shader, fragment shader, how this stuff is running on your GPU at a high level, and ultimately how do you get this rendering to the camera, and so that you can see something on your computer screen. And then I wanted to see how this big skybox was working. I looked at the light source, one big light source that makes a sun, and we looked at the materials and texture mapping and how UV mapping works, and the VFX systems, the little particle systems that are playing. All right, I'm gonna stop talking. and recover. But let me know if you have any questions. And have a good weekend. Thanks. Have a good weekend.